This is T. Padmapani from second year CSM. Under my CAA 2 assignment in advanced data structure and algorithm analysis. Today my topic is 0 by 1 knapsack problem using dynamic programming. 0 by 1 knapsack problem using dynamic programming. Introduction to the 0 by 1 knapsack problem. The 0 by knapsack problem is a classic optimization problem in computer science. It involves selecting a subset of items to maximize total value without exceeding a weight limit. The term 0 by 1 signifies that each item can either be included 1 or excluded 0 from the knapsack. Problem definition. Given a set of items, each with a weight and a value, the goal is to maximize the value. The knapsack has a maximum capacity which cannot be surpassed by the total weight of selected items. This problem can be formulated mathematically as an integer programming problem. Knapsack problem solution method 1. Capacity of knapsack m equals to 15. Number of objects n equals to 7. Weights of the objects w1 equals to 2, w2 is equals to 1, w3 equals to 5, w4 equals to 7, w5 equals to 1, w6 equals to 4, w7 equals to 1. And profits of the object p1 equals to 10, p2 equals to 15, p3 equals to 15, p4 equals to 7, p5 equals to 6, p6 equals to 18, p7 equals to 3. Object 1, 2, 3, 4, 5, 6, 7. Profit 10, 5, 15, 7, 6, 18, 3. Weight 2, 3, 5, 7, 1, 4, 1. Then we have to calculate the profit divided by weight. Arrange objects in decreasing order of P by W1 ratio as the following. Dynamic programming approach. Dynamic programming is an efficient technique to solve the 0 by 1 knapsack problem. It involves breaking down the problem into smaller subproblems and storing their solutions. The key idea is to use a table to keep track of maximum values for different weights and items. Dynamic programming types of approaches. Top down approach uses memoization, bottom up approach. Dynamic programming table construction. We create a 2D table where rows represent items and columns represent weights. Each cell in the table contains the maximum value attainable with a given number of items and weight capacity. The table is filled iteratively based on previously computed values, ensuring optimal. Recurrence relation. The recurrence relation for the 0 by 1 knapsack problem is critical to the dynamic programming approach. It states that the maximum value at a given weight can either include or exclude the item being considered. Mathematically, it can be expressed as V of I into W equals to max of V into I minus 1 into W. V of I minus 1 equals to W minus weight of I plus value of I. Base cases. Base cases are essential in establishing the initial conditions for our dynamic programming table. For 0 items or 0 capacity, the maximum value is always 0. These conditions serve as a foundation for building up to the solution of the full problem. Implementation steps. To implement the dynamic programming solution, we first initialize the table based on base cases. We then iterate through items and weights, applying the recurrence relation at each step. Finally, the result can be found in the last cell of the table, representing the full capacity with all items considered. Implement. How to develop and launch an optimized user experience. Produce guidelines for implementation, develop and launch final product or service, deploy a measurement framework. Time and space complexity. The time complexity of the dynamic programming solution is O of NW, where N is the number of items and W is the knapsack capacity. The space complexity can also be O of NW, but optimizations can reduce it to O of W using a single error. Understanding these complexities helps in evaluating the efficiency of the algorithm for large data sets. Applications of the 0 by 1 knapsack problem. The 0 by 1 knapsack problem has practical applications in resource allocation, budgeting, and finance. It's used in scenarios such as cargo loading, investment decisions, and project selection. Its principles can also extend to various fields, including operations, research, and computer security. Conclusion: the 0 by 1 knapsack problem showcases the power of dynamic programming in solving complex optimization issues. By breaking down the problem and utilizing a systematic approach, we can find optimal solutions efficiently. Understanding this problem is fundamental for those studying algorithms and computational theory. Thank you for giving this opportunity.